Hello, welcome to our presentation. We're going to be presenting on the Hybrid Anomaly Detection System to prevent malicious attacks on Automotive CAN Networks. So all of us are engineers at General Motors in the Detroit metro area. My name is Jonathan Cochran.
My name is Logan Coles.
And I'm John Mushat.
Alright, so let's jump into it. For the introduction, we're going to go briefly over what exactly is a CAN network, what is an ECU, some existing work that has been done in the area, why this work is important, and then what our goals are for the project. So, Logan, I'll let you take it away.
Yes. So, CAN is a controller area network protocol, and it was developed in 1983 by Robert Bosch, and it is still widely used in the automotive industry today. And so you have a two-wire system where nodes or ECUs are connected to these two wires, and they communicate on this CAN bus, where the bus acts as a wired AND channel, with a 0 being the dominant bit. And then ECU is an electronic control unit, and it's also often interchangeably used with a node in the CAN protocol. So an example of an ECU in the automotive industry would be a engine control module or a body control module, and each ECU has specific functions that it performs. So they're often domain specific. So an ECM would be sending out a signal related to potentially engine speed, whereas a BCM would be sending stuff related to the body of the vehicle. So if you go to open a door, there'd be a CAN message that gets sent out to notify that event occurring. Getting into how a CAN data frame is structured, the important fields that we're going to focus on are related to the arbitration field. So a CAN message does not contain address-related information. The way the protocol is set up is it's based off of this arbitration field. So when you have multiple nodes trying to access the CAN channel at the same time, there'll be a start of frame that is sent out, and that's used to synchronize communication across the nodes. And then each ECU that's trying to send a message will begin to send out its arbitration field. And then the way that a node knows it's won the arbitration process is during the process of sending out these 12 or 32 bits, depending on the way the frame is set up. As these bits are being sent out, the node is going to also listen and read back the bits after all 12 or 32 bits have been sent out. So if you have an engine control module sending out an arbitration ID, let's say 1, and a BCM sending out an arbitration ID 200, the lower arbitration ID will win and have priority and get broadcast on the CAN bus. So after the end of the arbitration process, the ECU that's able to read back the message that it sent out knows that it's then won the process, whereas if you have an ECU that reads back change and detects a change in bits, then it will know that it has to wait for the next idle period or for the next start of frame in order to try and rebroadcast its message. Additionally, the scope of this work came about looking at existing work. There was a team that proposed a two-stage anomaly detection system using a rule-based and also machine learning module. And so in their testing and report, they were able to prove that a decision tree, random forest, and XGBoost are efficient methods for determining on the Otis dataset whether or not a message is potentially a malicious attack or if it is a non-attack message. So the scope of our work came about as we are automotive engineers at General Motors, and cybersecurity is becoming an important part of vehicles today as modern vehicles are becoming more connected to the internet like everything else we see with the Internet of Things. So there's an increased need for security and reliability in the automotive network. So we propose and develop a method to try and take a machine learning model and rule-based filter and combine these two and make the size of the software and model small enough to be able to run on an existing controller within the vehicle. So overall, the goal is to simulate this anomaly detection system in a vehicle by combining these two filters, as I mentioned, and ultimately trying to make a lightweight model that's one, reliable, two, efficient at detecting attacks, and then three, able to run in the vehicle. And during the development of our model and testing, we encountered an issue where there is a message authentication that occurs within our vehicles, and in order to bypass or get around this message authentication, we would need to have a ECU team develop a specific software set that we'd be able to run in order to bypass this message set. So within the scope of our project and timeline of generating these changes, we were not able to take our model and run it on a vehicle, although this lies in an opportunity for future work. So we were, however, able to evaluate our model using Python and a CAN-based library to simulate our anomaly detection system.
Thank you, Logan. So moving on to the methodology portion. So we'll go over some attack types, what is in the rule-based model, what is in the machine learning model, and then also how the CAN network will be set up for our project. So briefly going over the attack types. So there are 3 attack types within the system of the OTIDS dataset that we'll be looking at. One is the DOS, or denial of service, where it floods the network with a bunch of messages, as can be seen in the left diagram. So a bunch of packets flood the system, and that will either delay messaging between ECUs or shut down the system completely. The next type of attack is the fuzzy attack, where a malicious node will sniff the network and create a randomized CAN ID and data payload based on messages that are already in the network. So it can pretend to be a message and infiltrate the system that way. The next method is the impersonation method, where a malicious node will stop messages that are being sent from one node and then copy those messages with whatever else it wants to include in it, and insert those messages back into the network and send those on to a target ECU. And then moving on to the rule-based model.
So in order to detect and potentially combat these 3 types of attacks, we implemented 2 filters, the first being the rule-based model. This is essentially a static rule set that is very dependent on the context of the CAN network, so essentially what ECUs are going to be present on it. But in general, we have 3 fields or 3 types of analysis we can do on the messages in a static method that can give us a good idea of whether or not a message is going to be a valid message or an invalid one. The easiest being arbitration ID. Essentially, within a CAN network, there's going to be a known set, a limited set of IDs that are valid within the system. They're going to correspond to certain ECUs performing certain actions, and the network's going to know from the get-go that these are valid. And any ID that comes in that is not part of that set is going to be immediately flagged as invalid, and we can either remove it or flag it for further processing. The next analysis was going to be the message frequency. So, for instance, with an ECM or an engine control module, we know that there's going to be roughly maybe 3 or 4 messages every 100 milliseconds or a single message every 100 milliseconds. So we can expect that each ECU ID corresponding to the ECM is going to occur at a periodic frequency, and we can measure the deviation between positive or negative between that to see if the messages are either being tampered with, so they're going to be delayed, or if they're just being straight up removed and we're seeing messages come in earlier or later than they should be. And if they do violate that, we'll also flag or remove them. And lastly, we have the sequence ID. This can be generally seen as, say, you're opening your car with your key fob, you open the door, you turn the car on, you shift the car from park into drive. It's a known sequence of actions that are very common, so it's something that we can essentially predict that if we see a certain sequence of IDs, we know that the following ID, there's going to be 3 or 4 following commands that are going to be related to that sequence. And if we start to see IDs either in between or after that don't correspond to that sequence, it's potentially a malicious actor either removing or adding messages that don't belong there, and so we can flag that whole sequence to be potentially malicious and thus identify the ECU that's at fault.
So onto the machine learning model. So this is trained on the OTIDS dataset, and within that dataset there are 4 sections: the attack-free, and then the 3 attack types. So the number of instances for each dataset can be seen on the table on the right. And then for the feature extraction, extracting the important information about these messages, there is the timestamp, the CAN ID, the DLC, and then also the data payload. So some algorithms were run to extract this information and put it into a processable state. Next, for data processing, a couple of these features are not in a numerical format. So some additional data processing was done to move them into a numerical format. That would be the CAN ID and the data payload. And then for the classifier model, this was done similar to the previous research where we implemented a decision tree, random forest, XGBoost machine learning techniques into an ensemble model, and the way that works can be seen in the diagram on the right, where they all feed into it, and then it selects the most voted on prediction from there. And then we also did hyperparameter tuning to both increase the accuracy a little bit, but mostly to reduce the model size so it can fit on an ECU. And this was done by iterating through ranges for each parameter, and these parameters were determined by going through the documentation that was available on the Python website. And then example for this is XGBoost, where the number of trees was modified to the optimal value, and additional tuned parameters can be found on our GitHub repository.
So lastly, we have the actual CAN network to simulate the CAN environment, since we weren't able to get into an actual vehicle. So in the CAN network, you're going to have quite a few ECUs, and in our system we also have a gateway. So this is going to have the engine control module, body control module, and also a TCM or transmission control module, in addition to the gateway. So the gateway acts as sort of a router or a firewall that all ECUs individually send their messages to, and then the CGM or the gateway routes all those messages to their appropriate targets, or really the rest of the network, since it's a no addressing scheme. So then for this, the gateway is going to also have the rule and ML filters built into it, since it's a centralized filter where all the messages will get filtered through that stage and then propagated out if they're passed or if they're recognized as valid. So for the actual testing, we randomly select 10,000 messages from our data set that is comprised of both the OTID messages and then also interpolated messages from that data set to generate some randomness and further evaluate the system. So these messages are then propagated through the system, through the simulator. The gateway processes them, flags it as either valid or invalid, and then lets them go throughout the network again.
All right, so moving on to the results section, we'll go through some results from the CAN network and then also results from machine learning model training.
So to start off, we have the actual rule-based filter. So from testing, it actually turns out that with the relatively simplistic rule-based filter that we implemented, it's actually not super efficient at marking some of these messages, mainly the frequency type being the largest category that we've captured, followed by the invalid ID and then invalid sequence. It really only captured up to around like 2,000 messages out of the roughly 4,000 to 5,000, depending on the data set. And then the ML filter was actually just significantly more efficient, so usually 2 times as good, reaching up to like 80-85% on good runs. The rule-based filter essentially would need to be more better designed to the actual CAN network, and just having a better schema and context to design the rules around, which would probably boost the accuracy and then reduce the workload on the ML portion.
So for the ML model, it was trained in about 250 seconds, so pretty quickly. And then from the confusion matrix, you can see the attacks and no attacks in the binary values, where it has pretty good results for both of those in terms of positives and negatives. And then the validation equations were used from the prior work to evaluate on the same metrics, and those are the accuracy, detection rate, false alarm rate, and F1 score. And these validation results can be seen in the table below. And then for the hyperparameters, we tuned several parameters for decision tree, random forest, and XGBoost. And by tuning these to these specific values, we were able to reduce the size of the model from 698 megabytes to just 5.1 megabytes. And this was exported into a pickle format, which can be used on an ECU.
And so then, in conclusion, our ADS performance for classifying an attack using our machine learning filter, we were able to determine that it performed vastly better than the rule-based filter. However, when combining these two filters together during simulation, we proved that the performance was approximately 85% efficient in identifying an attack from a malicious message. And then this leads into the opportunity for future work. So one opportunity is we can work with ECU teams at General Motors, such as the ECM team, to develop a calibration set to disable the MAC check at the ECU, basically allowing us to take our model, run it on a computer, connect to the vehicle using a NeoVi, and then running Vehicle Spy to basically send and monitor messages that are being sent over the CAN bus. Another opportunity for future work would be to develop more rules that are based around the controller that we are running it on, and then also further tune the machine learning model to reduce the size and create a universal format.
All right, so that's our project, and thank you for listening.